Okay, it's on. Hello. Okay. Okay, great. Oh, great. Okay, let me turn it off. Works.
Thank you. Okay, welcome everyone. The first talk of the session is by Qipeng Liu, who's going to be talking about quantum algorithms for variance of average case lattice problems via filtering. Please go ahead, Qipeng.
Okay, so it starts, right? Okay, great. Okay, so I will be talking about this quantum algorithm for variance of average case lattice problem via a technique called filtering. And this is joint work with Yilei, Chen, and Zhandry. So okay. So in this talk, I will basically record the two specific lattice problem, namely the short integer solution problem and the learning with error problems. So I will then introduce the variance of these two problems and show our algorithm that solves them. So although our algorithm is novel and solves different lattice problems in interesting parameter regime, none of the results gives application to solve shortest integer solution problem. So which is the most fundamental lattice problem. So I would say so I would like to say our work does not solve SVP, but still provide interesting direction towards this ultimate goal. So I think it might be inspiring. So here, let me briefly introduce lattice, and we will need this background for the last part of our discussion. So if you have attended a great tutorial by Packard, you probably will find that's familiar. So lattice is generated by a set of bases, and given k-linearly independent vectors, the lattice generated by them is basically all the integral linear combination of all the vectors. So this picture demonstrates a simple example of lattice formed by two vectors, B1 and B2. So here's the most fundamental problem, which I've already mentioned. It's called a shortest vector problem. The problem is to giving you a lattice basis to find the shortest non-zero vectors in a lattice. So you may ask why we can just pick the smallest vector in the basis and just output that. So the answer is fairly simple because you may encounter some very bad bases. Here's an example that's demonstrate two equivalent lattice. They're like both described like Z V2, but for the left one, they have like a very simple and very well structured basis. And for the other one, it will be relatively more difficult to find a short vector. Okay, so and this problem is actually an easy two-dimensional space, but it will becomes intractable when the dimension grows. And relative to that problem, there's another problem called approximated SVP. The problem is parameterized by a number R, and the problem is to find a non-zero short vector of length within R times the shortest vector in the lattice. So for different approximation factor, this picture demonstrates the difficulty and applications of this approximation SVP problem. And this explains why lattices are important to computer scientists. So there are like different views, and one way you can look at that is to look at this a constant approximation factor. That is, this SVP problem is NP hard if you want to get any constant approximation. And for cryptographers, we are more interested in break certain crypto encryption scheme or like building crypto based on lattices. And we can show that breaking certain public key encryption scheme is as hard as solving almost like linear approximation SVP problem for all lattices. In other words, it's like a worst case thing. So in this talk, I will particularly focus on two problems. One is the short integer solution problem. The other one is the learning with error problems. And Okay, so there are like the two average case lattice problem. I will explain the connection between that the SVP and them later. So the short integer solution problem is to give a random a of roughly this dimension and to find a non-zero integer solution x such that ax equals to 0. So far, this is not a hard problem since this is like an overdetermined linear system. You can solve that by doing a Gaussian elimination. So there's an additional constraint and make this problem hard. That is, the solution x should be short in some sense. So, and this will fail the trivial Gaussian elimination problem because usually if you find a random solution, the solution will be relatively large. And Zhandry formally proposes following problem in 1996. And the problem is called short integer solution problem. That is giving you a random matrix of dimension n by m, and m is usually n log n. Then the goal is to find a vector in the kernel of A and with a relatively short L2 norm. And it should be a non-zero vector, of course. Okay, so this is the short integer solution problem. Okay, so let's turn to the other problem, which is the learning with arrows. The learning with arrow problem asks you to find a secret vector S given an oracle. So this oracle is like a button. Every time you click this button, the oracle will return the random linear combination of this secret vector S plus a small amount of noise. So more formally, every click will give you an AI and YI. Well, AI is a random vector and YI is an inner product between AI and the secret vector S plus a noise. And this noise is usually drawn from a discrete Gaussian distribution. And also note that if there's no noise, it's also very easy. You can just do Gaussian elimination. Okay, so there are the two problems. So then why our cryptographers care about CIS and LWE problems? So there are a couple of reasons. The first reason is, of course, they are extremely useful for constructing crypto systems. For example, the basic crypto functionalities like encryption scheme and digital signatures, we can get them from the LWE and CIS. And even more interesting, with this rich structure of LWE, you can build all kinds of powerful crypto tools like fully homomorphic encryption, attribute-based encryption, and even like proof of quantumness and also like delegations of quantum computation. And so that's the first reason. And the second reason is this is conjectured to be hard for quantum computers. So I won't say too many words about that, but just look at this picture. This is like the second round of, it's maybe a little bit outdated, but the second round of this post-quantum crypto standardization. And almost half of the schemes are based on lattices or some variants of lattices. And the third reason is for some parameter regimes, this CIS problem and LWE problem, their average case hardness can be based on solving the worst case lattice problem, the SVP problem. So since many people believe this approximate SVP is hard, this gives more justification about the crypto systems and security of the crypto based on LWE and CIS. Okay, so that's all the reasons we care about CIS and LWE. So, and in this work, we will focus on variants of CIS and LWE problems. And we try to solve them by quantum algorithm using a novel technique we call filtering. So here we use the word variance. So in other words, that's definitely not the same as the problem I introduced before, but they are closely related. So let's first look at the first problem, the short integer solution problem. We just record, this is like the standard definition of CIS. Well, you are asked to find a small L2 norm solution in the kernel. And this is the problem we considered in this work. Here we consider a problem, well, this A could be very wide. A is like a very wide matrix. And you want to find a solution such that A times X is 0 and A is a non-trivial, non-zero solution. And besides, we have a requirement that the infinity norm of X should be bounded away from the largest C values in the field. In other words, the infinity norm of X should be bounded by Q minus C over 2. So in other words, you can take any values except the largest C values in the field. And there are some requirement on the width of the matrix A, roughly saying it should be roughly n to the C. So in other words, this basically says our algorithm only works if you want to have like a constant distance from this Q. In other words, like infinity norm can only be bounded like constant from the maximum Q. And as a corollary, we show that when m equals roughly n squared, we have a solution, we have an algorithm that finds a binary solution for Q equals to 3, which is not known before. So that is, I give you a linear system in F3, and the goal is to find a binary solution. You cannot have any 2 in your solution. So that's as a corollary. It's something new. Okay. So yeah, and that's the result of our SIS problem. And secondly, we consider a variant of LWE problem. And also we record this is the normal LWE. We are given classical samples, AI and YI, and the goal is to recover the secret vector. And the noise is usually drawn from a Gaussian distribution. And okay, so then the problem we consider here is something what we call LWE with quantum samples, or SLWE for short. So instead of giving classical samples, now we are given quantum samples. So every sample consists of these 2 parts. The first part is this AI, which is the same as the classical case, that is a random vector. And the second part is no longer a classical, like a classical inner product plus noise. It's now actually a quantum state that's like centered at this inner product, but with an arrow amplitude around that. So one observation is that if you get such a sample and you measure that in a computational basis, you will get a LWE sample roughly according to distribution F squared. So there will be a connection between this SLWE with arrow amplitude F and the regular LWE with arrow distribution F squared. Okay. Okay. So the problem is to give a like polynomial many such samples and to recover the secret vector S as usual. So our results shows that there's a polynomial time algorithm that finds the secret vector if the 2 following conditions hold. The first one is the DFT of F is inverse polynomial, and we call that quantity eta. And the second thing is this M should be sufficiently large. I will explain next. So this DFT of F will basically define as we apply this Fourier transform on the function F, we'll get another function F hat, and we look at the minimum value of this F hat. And this is what we call the minimum norm or the minimum value of the F hat. And this is what we call this DFT of F or the value eta. And the M is the M depends on the inverse of this value eta. So that basically makes the requirement the DFT of F should also be inverse poly to make our sample is also polynomial. So that's the requirement. So in other words, we only manage to solve this F when it satisfies the DFT is inverse poly. Okay. So before I get into the details of the algorithm, I would like to remark that there's some difference between the previous work. They also called something like quantum LWE with quantum samples. So here, the problem defined by Grillo, Kranidis, and Vistra, they also define similar notion, but they actually have superposition in the samples in the random vector A instead of the error distribution E. So it looks like similar, but for their problem, it's actually easy even if this error distribution are drawn from a Gaussian discrete Gaussian distribution. So, but however, I think their technique cannot be carried to our case. So I think there's 2 are imparable and incomparable. Okay. Okay. Yes. So right. So after the comparison, let's talk about how we do this. So we'll basically focus on this SLW problem because this problem can be reduced to the SLW problem for some distribution. So okay, let's look at what we do. So we're getting a quantum sample A and Y. We know that Y will be a sample that's centered at some S times A. So if we can figure out what is this S and A, then I mean, it's simple, just do Gaussian elimination. So then we look at a bunch of different quantum state. That is a quantum state that's centered at 0, centered at 1, so on and so forth. So we call them cat HT. So just say that's HT. So HT is basically a quantum state that's centered at T. So if all these HT are orthogonal, then the problem will be very easy. We just like construct a distinguisher or like a measurement that tells you what S times A equals 2, and we can do Gaussian elimination again. Okay. But the problem is, as you can see, these vectors they overlap with like very large fraction. So they're very much unorthogonal. The problem is to deal with that. So what we do is we first write down this matrix, HT to HT plus Q minus 1. They are the set of the independent vectors. They span the whole space, but they are not orthogonal. Then we apply the Gram-Schmidt and we make them orthogonal. And it's like the most brute force way to do that. So we get a bunch of orthonormal bases. And what we do is, okay, let's just measure on that basis. And we get a value. Okay. So the problem is when we get let's say the first row is outcome 0, the second row is outcome 1 for the measurement. So what we know is that if the outcome is 0, indicating it's in the space of HT, then we do learn nothing. This is because every vector will overlap with HT. So when the outcome is 0, we don't know anything, right? It can be any H0 to HQ minus 1. So when the outcome is 0, we just throw it away. But when the outcome is 1, we know that we get a little bit information. So what is the information? The information is this S times A is not equal to T. Because if that equals to T, it must, the measurement will always output 0. So it must not be 0. And similarly, if the outcome is 2, we know that it cannot be T or T plus 1 because it's not in the subspace spanned by these two vectors. And so on and so forth. So if the measurement equals to Q minus 1, we know that it cannot be this previous Q minus 1 possibilities. So it must be T plus Q minus 1. And this is what we call the filtering. That is, we filter out Q minus 1 possibility and we still get an equality. So the next problem is like, what is the success probability? Because we're doing Gram-Schmidt and maybe like with like overwhelming chance, it always outputs 0. So we never get any useful information. We can never get any equalities. So, and this is what we, our work on. So we basically show that for some specific distribution, we analyze the Gram-Schmidt matrix of this, the Gram-Schmidt of this matrix. And we show that, and specifically, this is a circular matrix if you look at that. So we show that for certain distribution, it is actually doable. For Gaussian distribution, it is not. Unfortunately, we find that for Gaussian distribution, discrete Gaussian, the running time is, I mean, this DFT is negligible. But for Laplacian and bounded uniform, it's actually non-negligible. So we can have a polynomial time algorithm for that. Okay. So since we don't have much time, I'm not going to record the whole algorithm. So, but still, I want to say like our result is if the DFT is non-negligible and M is sufficiently large, we can solve this quantum sample LW. And finally, I want to say that why our work does not solve SVP, because we know SVP connect to cis and LWE. So for cis, the problem is we have a pretty large L infinity norm, and that does not translate to a small L2 norm. And for LWE, we only know SVP to regular LWE, but not SVP to this quantum sample LWE. That fails these two approaches. And with that, I conclude my talk. Thanks.
Thanks for that nice talk. We have time for a few questions if anyone would like to ask.
Hi, thank you for the nice talk. So you mentioned in one slide that you considered various distributions for this function f, and
Yes.
you gave some examples like the Laplace distribution and so on. Is there anything known about the hardness of regular LWE, assuming these error distributions?
Unfortunately, we don't know because
Okay.
there's no, we don't figure out any connection between this classical sample and the quantum sample.
I see.
So what we do is we understand quantum sample with this specific distribution like Laplacian and bounded uniform.
Okay, thank you. And the second question, if that's okay, is can't you always, just starting from a regular LWE sample, construct a superposition sample by just like preparing like a superposition over like errors that are distributed with amplitude f, and then just add this into the classical LWE sample, and now you have like a shifted superposition sample. And if you set it up correctly, like this should be exponentially close to the superposition sample that you're looking at. So yeah, I'm just wondering like why the superposition sample is very different, or like why it behaves differently.
That's a good question. You're saying why we can just start with a classical sample and we propel like a amplitude
yeah, you can prepare like the superposition say that you showed shifted by a small error. And I claim that if the error is small enough that those will be exponentially close.
Okay, that's a good question. I haven't thought about that.
Okay.
Much, but we can.
Yeah, we can take it offline.
Okay,
Thank
yeah,
you.
thanks a lot for the great question. Yeah.
Does anyone else have a question? If not, I guess I have kind of an obvious question. Like, so this has not even a small implication for any crypto system, I guess, like not even polynomial speed up on the best attacks.
I mean, so for now, what we know is like, even if they're using like S infinity norm in many applications, they're still assume this F infinity norm is kind of small. But in our case, it's kind of large. I mean, you can come out with a scheme where this Q is relatively small, like constant, but then the algorithm will run into the Q. Well, I mean, Q can be a constant, but they're still like pretty large, which still does not give you any practical application, although it might be still polynomial time, like n to the 1,000, something like that. Yeah.
Thanks. Very, very interesting. Let's thank Qipeng again.
Yeah.